Yeah, thank you very much for inviting me. It's a real honor to be here, and thank you all for attending as well. I should mention, those of you, if anyone here is interested in my work in group theory, I'll also be giving a talk at the ENS on Tuesday afternoon. Okay, so my aim in this series of lectures is to tell you about some recent and, in fact, some brand new work as well in long-range percolation. So I was hoping to have all the papers online before I gave the lectures, and as always happens, that didn't work out, so they're not completely finished yet. But I hope that actually makes it more exciting for you in that you'll get to hear some things that you almost certainly haven't heard before unless you've been sort of following me around while I've been giving other talks. So my plan is today I'm going to start by just telling you about the big picture of what the conjectures are also for nearest neighbor percolation. In fact, this fits into just a very general sort of family of conjectures within statistical mechanics more broadly, like regarding self-weighting walk, the Ising model, and so on. And then I'll start telling you about long-range percolation, and then over the course of the week, I'll hopefully be able to actually prove to you many of these new results about critical long-range percolation. Okay, so I want to start by just saying sort of, again, the big picture. Okay, and I'll start by talking about nearest neighbor percolation on the grid, just to be concrete. Although, as I said, a lot of what I'll say has analogs for other models, so I'll say a bit about that as we go along. Okay. So I'll talk about Bernoulli bond percolation. Okay, so what that means is we have a graph. And for our purposes, we can always take the hypercubic lattice. And we have a parameter p in 0, 1. And we independently delete or retain the edges with retention probability p. Okay? So some standard jargon that is always used is that the edges that we retain we call open, and the edges that we delete are called closed. Okay? And generally speaking, what we're interested in the geometry of clusters, which just means connected components. Okay, so we start with this graph, like the hypercubic grid, for example. We randomly delete some of the edges, and then we want to understand, what is the geometry of this random subgraph that we have left over. Okay. Good. So, you can ask, why study percolation? Well, percolation is a sort of paradigmatic example of a model undergoing a phase transition. Okay? And it's arguably the easiest such model to define. And so there are other models that are arguably more important within mathematical physics, like the Ising model, for example. The Ising model is a bit harder to define. We may discuss it later on. The advantage of percolation is because it's so simple, it very often appears in other contexts as well. So, if you're proving something about some other kind of statistical mechanics model, there may often be some comparison to percolation. You can do something like that. Okay. So the first sort of basic theorem that makes the model interesting in some sense is that when D is strictly larger than 1, percolation has a phase transition. So what do I mean by that? Oops. So we can define PC, which will depend on the choice of the graph. So let's suppose for now that we're only going to consider infinite graphs. You can also consider phase transitions on finite graphs, but they're somewhat more subtle to define. So we'll define PC to be the infemal value of P such that infinite clusters exist, almost surely. Okay? Now, one thing to notice straight away is, of course, the existence of an infinite cluster is a tail event, right? So I can think I have my graph, I have all these independent coin flips on each edge. This event does not depend on any, if I change the status of any finite collection of coin flips, it does not change whether this event holds or not, okay? And it's a famous theorem of Kolmogorov that any such event, any tail event for independent random variables has probability 0 or 1. Okay, so this event that infinite clusters exist is actually a 0-1 event, so you could replace this almost surely with positive probability. Okay, and you get the same value of PC. Okay, of course, whether a particular vertex belongs to the infinite cluster is very much not a tail event. You know, that will have probability between 0 and 1. Okay, and the theorem is that, more precisely, PC of ZD is strictly between 0 and 1 for D strictly or greater than or equal to 2. Okay. On the other hand, of course, PC of Z is 1. You know, this is not very interesting in one dimension. If you're deleting any edges at all, well, you know, there are only two ways to go to infinity, right? You start at the origin, you can either go to the right or to the left. If P is less than 1, eventually you'll find an edge that you can't cross in both directions, okay? So one dimension from the perspective of the nearest neighbor model is not really interesting at all, or at least we won't have a phase transition. But once you go to 2 dimensions and higher, you do have a phase transition. Actually, you know, I'm mostly going to be talking over this course about long-range percolation. Once you start looking at long-range models, one dimension is just as interesting, more or less, as a general dimension. Okay. Good. So why is this true? Okay. Well, the first basic thing to notice is that the positivity of PC is something that's very easy to establish. Okay? So if, let's say, let G be a bounded degree graph, so as a reminder, the degree of a vertex in a graph just means the number of edges which are adjacent to that vertex. So bounded degree means there's some finite constant that bounds all the vertex degrees. Okay? So the claim is that PC of G is always at least 1 over the max degree minus 1. Okay? In particular, it's positive. Okay? So why is this true? This is a very easy argument. The idea is, well, I could define PC equivalently as the infemal value of P such that at least one vertex has positive probability of being an infinite cluster. Okay? Now, of course, being an infinite cluster is equivalent to, by a standard compactness argument, to saying that there exist simple paths of any finite length starting at that vertex. Okay? So what we can do is, you know, fix some vertex, right? And look at the expected number of open simple paths of length n. Okay? Well, you know, if I give you a simple path, so simple, I just mean it doesn't return to the same vertex more than once. If I give you a simple path, the probability that it's open is just p to the number of edges, right? So this is p to the n times just the number of, let's say, sorry, open simple paths of length n starting at x. Right? So it's just p to the n times the number of simple paths of length n from x. Okay? But of course, you know, this is very easy to bound using the bound on the degree. Right? So this is bounded by p to the n. And then, well, for the first edge of the path, you'll have the degree many choices. And every subsequent step, you know, you can't go back the way you came from, so you'll get one less choice. So if so we can bound this by max degree times max degree to the n minus 1. Okay? So in particular, so if p is strictly less than 1 over the max degree minus 1, then this expected number of open paths from x, well, it goes to 0 at length n. Okay. In fact, it goes to 0 exponentially quickly. Okay? But of course, the probability that you have at least one open simple path, right, we can use Markov's inequality. So, you know, the probability that there exists an open simple path from x is bounded by, of length n, sorry, is bounded by the expected number of such paths, right? That's just Markov's inequality. And so this goes to 0, and therefore you don't have an infinite cluster. Again, if you did have an infinite cluster, it must contain an infinite simple path. That's a classic compactness lemma in graph theory. Yeah.
Yeah, I think you forgot minus 1 here in the down to the max. This one. Yeah?
This one?
Max degree times.
Oh yeah. Sorry. Thank you. Yes. This is also true, but yeah. Okay. Okay, very good. Okay. So how do we prove the theorem? Well, the harder part of the theorem is showing that you actually have this supercritical phase. Okay, so the terminology, but maybe I should say, in general, we have these two phases, and you know here we have we'll call this subcritical and this supercritical, and this is critical. So the harder part, generally speaking, is to establish the non-triviality of the supercritical phase, i.e. that PC is strictly less than 1. So in the context of ZD, this proof I'm about to show you goes back, I think, to the original work on percolation by Broadbent and Hammersley in the 1950s. Although the argument is really what's known as the Piles argument. So this is a proof that Rudolf Piles came up with to prove the non-triviality of the phase transition for the Ising model. In fact, on any graph, whether you have a phase transition for percolation and an Ising model are always equivalent. So you can do either whichever version of the proof you like and then just use the equivalence. But let's, I think the percolation one is simpler. So what's the Piles argument? Well, the idea is basically, well, first of all, we can observe that, well, if I look at the d-dimensional hypercubic lattice, it actually contains the two-dimensional hypercubic lattice as a subgraph, right? So of course, of course, if I just think about this two-dimensional plane sitting inside my d-dimensional space, if I have already an infinite cluster within that 2D plane, then I also have one in the whole space, so it suffices to prove the theorem in the case d equals 2. In fact, the same argument can be made to work for higher dimensions directly, but it's combinatorially a bit more fiddly to write it down properly. Okay, so it suffices to consider d equals 2. Okay, and here's the idea. So in the two-dimensional case, we have a lot of additional tools available to us which we don't have in general. In particular, we have planarity and therefore planar duality. Okay, so what we can do is say, if the origin belongs to a finite cluster, there must be a closed dual cycle surrounding it. Okay, so here's the picture. I have the origin. I have some finite cluster that it belongs to, which might have some holes in it or something like that. Okay, but if I look at all the edges in the boundary of this cluster, so they must be closed because they're in this outer boundary of the cluster at the origin. Okay. Now in the planar dual, I can consider all the dual edges which cross these outer boundary edges orthogonally. Right, so it looks something like this. Okay. So what you see is you get a path in the planar dual, which in the case of the square grid is just another square grid, which goes around, surrounds the outer boundary of this cluster. And all of those edges are they're dual edges that are crossing one of these closed edges in the original graph orthogonally. Okay? So what I can do is I can do a very similar argument, but I can count the expected number of these all closed dual circuits. Okay. So again, the probability that if I give you a specific one of these dual circuits surrounding the origin, the probability that all of the primal edges that it crosses are closed is 1 minus p to the n if it has length n. So I'm going to sum over the length. How many dual circuits are there of length n? Well, I can think about the slight subtlety compared with this case is I don't know where these circuits start, right? But of course, if I have a dual circuit that surrounds the origin and has length at most n, then it must intersect this positive real axis somewhere within the first n steps. Okay, so I have at most n choices for where I intersect this axis. Then once I have that, I have at most 3 choices for how to extend the path. Right? If I start my circuit here, and each choice I can choose to either continue straight, turn left, or turn right. Okay, so I get a simple bound like this. Okay, now of course this is not a sharp bound at all, but that's not the point of this, right? We're not trying to really compute anything exactly, and in fact, you're not really going to be able to compute PC exactly via this kind of method. So this is just a crude bound. Okay, so we get the expected number of these closed dual circuits is bounded by this. In particular, if p is close enough to 1, this expectation is less than 1. This is overkill. In fact, really, you just need this expectation to be finite, and then you can argue that you have to have a positive probability of not having any such dual circuits. But let's just make the expectation less than 1, just to make things easy for ourselves. Okay? If it's less than 1, then the probability that there are no dual circuits, well, the probability that there exists a dual circuit, a closed dual circuit, is bounded by this expectation. So it's less than 1 also. Okay? And if there do not exist any closed dual circuits, then the origin must belong to an infinite cluster. Okay. So again, these things are very, very classical. As a historical note, so Piles proved this, I think, in the 30s for the corresponding statement for the Ising model. There's an interesting history where Ising himself was a PhD student of Lenz, I think 10, 20 years before the work of Piles, and he proved that the one-dimensional Ising model does not have a phase transition. And for some reason, this led the whole physics establishment to write off the Ising model as uninteresting. Sort of remarkably now, because it seems very obvious from our modern perspective that, okay, one dimension is just not the right thing to look at for these kind of things. But it wasn't until this subsequent work of Piles, again, some decades later, who proved that there is indeed a phase transition for the Ising model and reignited interest in all these kind of things. Okay. Okay. So that's the first basic thing. And again, from my point of view, this theorem is what makes percolation interesting, sort of makes it worthy of study, if you like. Okay? And basically, the whole course, what I want to focus on is what happens exactly at this critical point. So what can we say about critical percolation? Okay, so I should say there are also very similar questions one can ask about what happens when P is just very close to PC, some of which we'll also encounter, and they're similarly interesting, and usually understanding P very close to PC and understanding exactly PC are closely related problems. Okay. Let's see if I can. Use the space. Oops, sorry, didn't know that was going to happen. Okay. All right, so the first, qualitative question that one can ask is, do infinite clusters exist at PC? Okay. So PC is defined to be the boundary of the regime, these two different regimes where you do and do not have infinite clusters. So the first thing you might want to understand is that which of these regimes does it belong to in some sense. Okay. And basically the conjecture is that no infinite clusters for all D at least 2. And this is known for D equals 2, where it's a corollary of a theorem of Keston, or maybe I'll say it's also due to Harris. To give a bit more detail here, it was conjectured for many years that the critical probability of the square grid is exactly 1/2. Okay? And this is what was finally proven by Harry Keston in 1980. Okay? Now, the reason why you get 1/2 here is the critical probability for the square grid is essentially a consequence of the fact that the square grid is its own planar dual. Okay, that's sort of why you get 1/2 having a special role. Okay, now, and in terms of why it implies there's no infinite clusters at PC, well, in fact, Harris had proven, I think, in the 60s that there are no infinite clusters on the square grid at 1/2. Okay, so together with Keston's theorem that PC is equal to 1/2, that shows that there's no infinite clusters at PC. So one thing I want to point out about this is the fact that you can exactly compute PC in this example is highly atypical. Okay, so, well, if you look at other planar lattices, like the triangular lattice or the hexagonal lattice, things like that, then you can also compute PC. But beyond those kind of examples, or trees, things like that, beyond a few special examples, you will not be able to compute PC. Okay, so for example, if you look at, if you want to study percolation on the cubic grid, PC of the cubic grid is some horrible number that, you know, there's no reason to suspect it has any kind of closed form expression. And in some sense, trying to study the value of PC is sort of the wrong question from many perspectives. Okay. I should say, you know, of course, numerically, it's an interesting question, you know, computationally to estimate these things. And, you know, there are ways that you can get not with any rigorous error bounds, but you can compute PC of Z3 to like 12 decimal places, something like that, numerically. But it does not appear to coincide with any nice number. Okay. Now, the other case, it's known as when D is very large. Okay, and I'm going to, of course, being much larger than 6 is the same as being much larger than 1, but 6 has an important role to play here, as we'll see. Okay, and this was proven by Hara and Slade in 1990, and I'll say much more about this soon. And, you know, in some sense, morally, we just need D strictly larger than 6. Okay? The reason why 6, and I'm going to talk about this a lot soon, is that there really is a change in behavior of the model at 6 dimensions. So the model in strictly more than 6 dimensions is really just significantly simpler, easier to understand than the low-dimensional model. Of course, 2 dimensions is also very special for some quite sort of complementary reasons. So in this paper, what they actually show is that, well, they say for the hypercubic grid, if the dimension is at least 19, then you have no infinite clusters at criticality. That has now been brought down with computer-assisted proofs for numerical optimization by van der Hofstad and Pfitzner. They can now get it to D at least 11. Okay. Now, why do I say morally D is bigger than 6? Well, this restriction is essentially the method that they use, something called the Lace expansion, is a method that requires some small parameter, which could be like 1 over the dimension, but it doesn't have to be. You can also take it to be something else. So another case they're able to understand is if you fix just a dimension strictly larger than 6, but instead of looking at the standard hypercubic grid, you look at a different graph. So for example, you could take all these integer lattice points of ZD, but then form the graph where any 2 points are connected by an edge if they have distance at most L from each other. Okay? And what they prove, if D is strictly larger than 6 and this parameter L is sufficiently large, then you can prove everything. So again, morally, this method works strictly larger than 6, but it also requires these numerical assumptions, basically, that prevent it from being applied all the way down to 6 in the standard lattice. Okay. Okay. And this is open for D between 6 and 3. Okay. Now, the point of this course, though, is not really to talk about this qualitative question. It's to talk about what we would like to do after solving this qualitative question, which is to try to understand quantitatively what does the model look like at criticality. Okay? And basically the idea is that at criticality you should only have finite clusters, but you should have very large finite clusters. So, you know, if you look at a large box or something like that, you'll see these kind of macroscopic fractal-like clusters that occupy, you know, they'll have 0 density within the box, but they'll be geometrically large. So, you know, they'll have diameter ordered the box, for example. And these large critical clusters should have very interesting fractal geometry. Okay? And this is something we want to understand. And we're going to try to understand this primarily via critical exponents. Okay, so the idea is that many interesting quantities which could describe some tail probabilities at criticality, or you might have some quantity that blows up or goes to zero as you approach criticality. Many interesting such quantities should have power laws describing them. Okay. Now, often these exponents in the power laws, you could also interpret them geometrically in terms of the dimension of some kind of fractal set in some continuum limit. But let's, for now, just think about these as just numbers. Okay. So, for example, so one of the most important things to understand is called the two-point function. Okay, which is just the probability at PC that X is connected to Y. Okay, by an open path. Okay, and this is one of the many things that we believe is described by some kind of power law. And I should say that all these power laws have there's traditional notations for all of them. So if you want to become a master of this subject, one of the things you have to do is memorize all these different notations for exponents. I should say one of the problems with this, it will often be the case that the standard notation for the exponent will overlap with a Greek character that we're also using for something else. So I apologize about that. It's something you get used to if you work in this area. So, okay. So one of the examples here is that this two-point function should decay like a power of the distance. Okay, and this has a traditional name for this power, which is minus d plus 2 minus eta. Okay. By the way, one of the reasons to use these traditional names for the exponents, like eta here, for example, being written in this particular way, is, and I think this notational conventions were introduced by Fisher in the physics literature, is that they actually allow for the correct comparison of exponents between different models. So people sort of figured out which exponents should be interpreted as the same exponents between percolation and Leçons model, for example. And if you use these notational conventions, then you will automatically be making that identification in the right way. Okay. So this is one example of such an exponent. And I'm going to leave the meaning of this notation. I'm going to reserve this for, there'll be other things we'll use, like more standard asymptotic notations on. I want to keep this squiggly one as just not having a fixed meaning. It's just, this should behave something like this in a way that I maybe don't want to say precisely what it means yet. Okay. Another example is the volume tail. So at criticality, so I'm always going to write K for the cluster of the origin. Okay? And similarly, I'll write Kx for the cluster of X. And, this absolute value just means the number of vertices in the cluster. Okay? So if you look at the probability that the cluster at the origin contains at least n vertices, this is another one of these quantities that's expected to be described by a power law. In this case, the traditional name for this is 1 over delta. Again, delta here does not mean a small number, it's just a number. Okay. Another one is what's called the susceptibility. Which is just the name for the expected size of the cluster at the origin. Okay? And again, this should have a power law behavior. In this case, it's not a tail of a probability, it's how this blows up as you approach PC. So by the way, it's an important theorem which we'll discuss in more detail later, called the sharpness at the phase transition, that the expected size of the cluster at the origin is finite if and only if P is strictly less than PC. Okay, and as you approach PC from below, this should blow up like some power of epsilon, And the traditional name for this exponent is gamma. Okay. Now I could keep going on for some time and introducing more of these. Maybe I'll just say one more, which is that if you're slightly above criticality and you look at the probability that the origin belongs to an infinite cluster or is connected to infinity, then this should go to 0 like some power of epsilon, and this is denoted by beta. Okay, so one thing to stress about the fact that I'm being vague with the precise meaning of this is that in all of these cases, you sometimes get logarithmic terms. Okay, so it might not be exactly like a power. One precise meaning you could take for everything that I've written on this board, but perhaps not every time I write this symbol, is that if you take the logarithms of both sides, the ratio converges to 1 in the appropriate limit. Okay. Good. Okay. So you know, I mentioned before about this work of Haar and Slade, where they prove that there are no infinite clusters at criticality in high dimensions. By the way, I should say this statement that there are no infinite clusters at criticality, this is often referred to as the continuity of the phase transition. I'll almost certainly say that at some point, so it's best that I say now what it means. The reason why it's referred to as continuity, well, one reason is that it exactly corresponds to whether this function is continuous, the probability that the origin belongs to an infinite cluster, which you can think of as the density of the infinite cluster. Okay. So as I said, they proved that in high enough dimensions you get a continuity of the phase transition, but in fact their proof establishes a lot more than this. It tells you all about all these critical exponents and so on. Okay? And what happens is that in fact once you go to high enough dimensions, these exponents start taking simple values. Which are known as mean field values. Okay. This terminology mean field comes from the Ising model. It doesn't really make direct sense for percolation, but it's by analogy. Okay, so let me say what these are. So this is a theorem. So in fact, what Haar and Slade really proved is they established a sufficient condition that was already known via several previous works to imply these mean field critical values, which is called the triangle condition. But it implies in particular that so again, under the same assumptions I was saying before, so either the dimension is very large or you're just strictly more than 6 dimensions and you work with the spread out model, then for example, this volume tail is like 1 over square root n, so delta is 2. The susceptibility blows up like 1 over epsilon, as epsilon goes to 0. So gamma is 1. And the density of the infinite cluster is of order epsilon, at PC plus epsilon. Okay. By the way, this symbol will mean use another color. this does have a precise meaning. It means equality up to constants. Okay? So it means, you know, this is bounded above by a large multiple of this and bounded below by a small positive multiple of this. Okay? Now, one thing that they actually did not prove, I just realized I don't know whether you right. One thing they didn't quite prove in this paper was about the two-point function. Okay, so in fact, in this original work of Haar and Slade, their method was all based on Fourier analysis. So it didn't really allow them to get point-wise estimates on the probability x is connected to y, only on the Fourier transform of this function. And this was improved to a point-wise estimate by this later work, about 10 years later, I think, of van der Hofstad, Haar and Slade, who showed under the same conditions that, sorry, again, equality up to constants, that in high dimensions, the probability x is connected to y at criticality decays like their distance, the power minus d plus 2. So in other words, ether equals it. Okay. Now, this maybe I shouldn't have started by just telling you what the theorem is. I should say, you know, why should you expect these exponents, and like, what does this mean? What is the interpretation of these values? Okay. So, well, one thing to notice straight away is that this scaling with minus d plus 2, this is the same order as the Green's function. Right? By which I mean here the lattice Green's function. So gxy is the it's the expected number of times that a random walk started at x visits y. Okay, that's you know, sort of in some sense the reason why we have this particular notational convention for eta, where we write the exponents as minus d plus 2 minus eta. It means eta is the correction to Green's function scaling, which is sort of the simplest scaling that you can expect for these kind of models. Okay, but then of course the question is, well, why should you expect these connection probabilities to look like the Green's function in high dimensions? So the idea is that high dimensional percolation behaves roughly like branching random walk. Okay. So what do I mean by that? So what is a branching random walk? Just call it BRW. Okay, so it's a process with an evolving cloud of particles. Where each step of finitely many particles, at each step, each particle splits into a random number of offspring independently. And then, as part of the same time step, each offspring does a random walk step. i.e., it picks a neighbor uniformly at random from where it currently is on the lattice and then moves there. Okay? So, equivalently, you can first sample the genealogical tree of the particles. So in other words, you forget about the fact that the particles are also undergoing the spatial motion, and you just form this tree of parent-child relationships. Then embed into the lattice uniformly at random. Okay. So this gives you, another statistical mechanics model. It's critical when the expected number of offspring is equal to 1. Okay? In the sense that if you have less than one child in expectation, then the process will die out very quickly. If you have more than one child in expectation, it has a positive probability to survive forever. If you have exactly one offspring, then you're critical and you get all these kind of power law type behaviors. Okay? And for this value, the expected number of particles that visit X when you start the process at Y is actually just exactly equal to the Green's function. Okay? Why is that? Well, it's actually just a consequence of the linearity of the expectation. If you have a mean 1 number of offspring, if each particle has mean 1 offspring, then actually the total expected number of offspring at generation n is exactly n. In fact, whatever this is, you get that to the power n, right? Just by a simple induction. Okay? So you get that the expected total number of offspring at time n is exactly 1 at criticality. So, but of course, each one of these particles in generation n of the tree is being embedded by a random walk into the lattice, right? So if you just use the linearity of expectation, you get this equality. You just get exactly a Green's function. Okay. Also, less obviously, but this is very classical stuff, and it's things that you could and many people do teach in undergraduate probability courses. If you, at criticality, the probability that the total number of particles ever, including summing over all generations, is at least n, is of order 1 over root n. Okay, I should say this is for finite variance offspring. Okay, so again, this other mean field exponent that I wrote down, the 1 over root n, that's again, you should interpret that as just being the same one that you get for the branching random walk. And in that case, the exponent, you don't even need to look at how the particles are embedded in space. It's just this 1 over root n that just comes from, it's just a branching process exponent. Okay, now in fact, all the other things I wrote there, that you also get the same answer in the branching process. Okay, so if you look at the expected total number of particles, well, as I said, in the branching process, if the mean is mu, you get mu to the n is the expected number in generation n. So if you sum over, you just get the geometric series, right? And of course that has this 1 over epsilon scaling as you approach 1 from below. And similarly, again, this is a less obvious thing, but it's still true. In the case of a finite variance offspring distribution, so you can just imagine bounded offspring, right? You either have 0, 1, or 2 particles, for example. You also get that the probability of that the process survives forever when you have mean 1 plus epsilon is also of order epsilon. Okay, so you can think, basically what this theorem is telling you is that all these critical behaviors for high-dimensional percolation are just the same as for the branching random walk, which is a sort of much simpler model. You can think of one way this would be described is that the branching random walk is sort of a non-interacting version of percolation. Okay, so that might sound a bit strange, so let me say how you could interpret that precisely. So one way you could imagine if you wanted to sample percolation on a computer, here's one way you might do it. You start with the origin, and then you look at all the edges incident to the origin, and you pick a Bernoulli random variable to decide whether they're open or not, right? And so you'll find that some of them are open, some of them are closed, and then you'll get this second step where you have all the neighbors at the origin that you found are connected, right? So you're doing, in other words, just a breadth first search of the cluster at the origin. Okay, and at the second step, you have these guys that you found in that first step, and then you repeat the same thing, right? You look at each of their neighbors, you check whether they're open or closed, and then you go to the third step and so on. Okay? Now, what you'll notice is that when you do this, of course, there are edges that you already checked, and therefore will not check again, right? If you didn't do that, if you, let's say you get ChatGPT to write this code for you and you don't check it. And then you might find, oh, actually, it didn't do this thing where it checked which edges I'd already queried. If you just keep reusing all the edges and ignoring whether you'd already queried them or not, you're exactly getting a branching random walk, right? So you can think that percolation is kind of like the branching random walk, except that particles get killed when they try to return to the set of already visited sites. Okay? So again, you can think it's like percolation is like branching random walk plus this self-intersection type interaction. Okay? So you can think what these theorems are telling you is that in high enough dimensions, that interaction is not important to the critical behavior. Okay? Now, one way you might think to prove this naively is to say, well, actually, what I've just described, it actually gives you a coupling between percolation and branching random walk. So for the non-probabilists in the audience, what does a coupling mean? It means you have two random variables and you want to somehow put them on the same probability space in an interesting way that lets you compare them, right? So in this case, we could define percolation and branching random walk on the same probability space in exactly the way I was just saying, where we do the simultaneous breadth first search, and in one case, we allow ourselves to go back to where we've already been, in one case we don't. Okay? And you can say, well, in that case, it's obviously percolation is just smaller than branching random walk, right? So you might think, well, I should obviously get that the percolation two-point function is smaller than the branching random walk two-point function. Okay, now that's not true. It doesn't work. Why is that? Well, it's because, of course, the critical parameters are different, right? So, it is true that you can do this point-wise comparison of percolation and branching random walk, exactly like I said, but it's not going to be critical and critical, right? Actually, if you do critical percolation, in this coupling, it would correspond to branching random walk at some supercritical value, and then, of course, you can do the comparison, it's just not going to be very useful, okay? So, in fact, this way of looking at percolation as an interacting branching random walk, it's very useful to get the intuition for like why this is happening, but it's not at all the case that the proofs work by analyzing this coupling. In fact, I don't think any of them work in this way, really. Okay, good. Okay. There's a similar point, by the way, in comparing critical phenomena between different dimensions. You might be tempted as well to think, well, if I know something about critical percolation in high dimensions, well, 2 dimensions is just like a subgraph, right? So maybe I can also just say, you know, shouldn't the clusters be smaller or something, right? Of course, that would be great if it's true. In fact, the reason the argument doesn't work is, again, it's the same one. It's the critical values are different. So of course, you could bound critical percolation in 2 dimensions by percolation at 1/2 in high dimensions. But percolation at 1/2 in high dimensions is going to be very supercritical. So this is going to not work very well at all as a way for you to bound things. In fact, in terms of what we actually see in the behavior of the models, the monotonicity tends to actually go in the opposite direction than what you might expect from these naive arguments. So it tends to be that smaller, lower dimensional graphs actually have sort of worse phase transition, like heavier tails and all that kind of thing, in the opposite direction to how you might expect from this naive way of reasoning. Okay. Good. So I should say as well that I mentioned that this work of Hara and Slade uses a technique called the lace expansion. And this was introduced by Bridges and Spencer in the 80s to prove similar theorems about self-avoiding walk, where, again, there you get this change of behavior in 4 dimensions, and actually, I'll say something more about that in a bit. Maybe. Okay, but yes. So you can think that this the lace expansion is sort of a systematic way of proving this kind of theorem, or at least it was after this first introduction by Bridges and Spencer in the context of self-avoiding walk. It was sort of developed into a systematic way for proving this kind of thing for many other models in the work of Hara and Slade, who also proved theorems about several other things too. Okay, and so the idea is basically it's a way of expanding over. You have some model you'd like to understand, like percolation, for example. You have some kind of reference model that is sort of non-interacting, like branching random walk, and in some sense you'd like to say that in high enough dimensions, these interactions have some sort of purely local effect on what's going on, and you're trying to kind of expand in terms of that microscopic interaction and say, actually, at large scales, it doesn't do anything. Okay. Now, this is a famously technical thing to actually understand properly, and I won't be going into this in this course. But basically, what it does is it gives you access to this kind of thing, like the 2-point function, or as I said in the original work, to the Fourier transform of the 2-point function. And once you have that, you can check these other exponents using earlier works. Basically, all these other things were known to hold under this assumption, for example, for d bigger than 6. Okay. So that is the high dimensional case. And of course, many of you are wondering, I keep mentioning d6, you know, what's the deal with that y6? So I'm going to talk a lot more about that later. Maybe one thing I should mention though now is that this general story where once you go to high enough dimensions, you get this simple mean field critical behavior, which means that the critical behavior becomes the same as in some kind of non-interacting, or people sometimes say like Gaussian version of the model. This is very common across many models of statistical physics. So here I'm talking about percolation, but for example, self-avoiding walk is in some sense the best example to talk about this picture in. So self-avoiding walk is just means you sample a uniformly random simple lattice path of length n, right? So if you didn't have this condition on it being simple, this would just be ordinary random walk. So you can think of it as conditioning a random walk not to return to the same vertex. The idea there is that once you go to high enough dimensions, in that case it's dimension 4. Well, if you looked at an ordinary simple random walk, well, the probability that it fails to intersect itself is always exponentially small. So whatever dimension you're working in, this is going to be a very heavy conditioning. You're conditioning on an event of very small probability, but somehow the nature of the conditioning changes a lot as you pass dimension 4. And one reason why you can think that that happens is that dimension 4 is the dimension above which two independent simple random walks intersect finitely often. Right? This is a sort of analog of the fact that will be more familiar to many of you that 2 dimensions is critical for a single random walk to return to the origin infinitely often. So 4 dimensions is the critical dimension for 2 independent simple random walks that intersect each other finitely often. And so the idea is that above that dimension, when you're conditioning on this thing that the path is simple, somehow the changes that you have to make to enforce that conditioning are very like microscopic, small scale things. So even though this event has exponentially small probability, the nature of how you're changing the measure is very different. Okay? Whereas in low dimensions, these paths are going to intersect each other really macroscopically. You know, if you take a long random walk, there'll be many times that are comparable to the total duration of the random walk where it's intersecting itself. Okay? So the nature of this conditioning will be very different. And basically, the story is that for all of these different models, there is an upper critical dimension above which you start getting this simple non-interacting type behavior. Now, the value of that upper critical dimension does vary between these different models. So for percolation, it's 6. For self-voiding walk in the Ising model, it's 4. For some other models like lattice trees, it's 8. So it can be various different things. In fact, 4 is, I would say, the most common value at the upper critical dimension, but it can be other things. Okay, and we'll come back to this question of why it's 6 for percolation later. Okay, so that's the high dimensional case. What about low dimensions? So the idea is once we go below the upper critical dimension, the model should really start to feel this effect of being in a finite dimensional lattice and start to behave really genuinely differently than it does in high dimensions. So the one case where we understand this well is dimension 2, where I have to refer to my notes to get these correct. So we get that it's known that delta, known again with some caveats, which I'll describe in a second, that delta is 91 over 5, beta is 5 over 36, gamma is 43 over 18, and eta is 5 over 24. Okay? And this is known for site percolation on the triangular lattice. So site percolation means that you randomly choose to delete or retain vertices rather than edges. Okay? And this is a culmination of works of many people. So Kasten, Lawler, Schramm and Werner, and Smirnov. Okay, and there's obviously a lot of interesting things to discuss here. I won't go into anything like as much detail as I might because it's not the focus of these lectures. But the first question is, of course, where are these numbers coming from? I mean, they're quite curious. This turns out to be kind of a characteristic feature of two-dimensional critical phenomena, that you get these slightly strange, complicated, rational values coming out for the exponents. Okay, and there are many underlying reasons for that. So I should say these were actually predicted sometime earlier than they were proven in the physics literature by Nienhuis using some non-rigorous methods. And ultimately, in two dimensions, there's just a lot of rich theory that's connecting this to other areas of mathematics. So, for example, there are strong connections between two-dimensional critical phenomena and conformal field theory, and with the representation theory of the Virasoro algebra. And ultimately, there's just a lot of special things going on. Of course, in 2 dimensions, you also have all the topological things, which are much more constrained than in general dimensions. You also have access to complex analysis, which underlies the connection, which really underlies, if you like, the proofs of these things, which all go through the connection to Schramm-Loeffner evolution. Okay, so essentially, the story here is that Keston, many years before these other works, showed that if you can compute any one of these exponents, then they all there are scaling relations between them. If you can compute one of them, you can compute all of them. Okay. Then Lawler, Schramm, and Werner showed that the exponents take these values, and again, really, they just showed that like, one of these exponents takes these values, and then you can use Keston's theorem to get the rest. If the model has a conformally invariant scaling limit, and then this last step, the fact that the scaling limit has this conformal invariance, was shown by Smirnov. Okay. So I should also say silly scaling limits. Okay. Actually, maybe it's a good time to mention, so I've been talking about things primarily through the language of critical exponents, but another way that you can think about what's going on in critical models is via what we call scaling limits. So what I mean by that is, you have these systems defined on a lattice, and one of the hallmarks of critical systems is that they have some kind of approximate scale invariance. Okay, so if you look at some very large scale and try to understand what's going on macroscopically, it shouldn't really depend on what large scale you're looking at. Okay? So, and consequently, there ought to be some way of taking a limit where you take the lattice spacing to 0 and try to look at some macroscopic features of the model that you find interesting and take some limit and get some continuum random fractal or something like that. Okay? So in the context of in 2D, the right way to do this is to look at interfaces and where these things of whether two like macroscopic shapes are connected to each other, things like that. And you can understand everything about the scaling limit through this SLE process that Schramm introduced. In high dimensions, this is actually the subject of some ongoing work I have with Arthur Blanc-Renaudy, and I apologize for my bad French pronunciation of his name. Where we've proved that in high-dimensional critical percolation, the large critical clusters converge in the scaling limit to something called super Brownian motion, which is the same thing which is the scaling limit of the branching random walk, which of course is what you would expect. So I may say something more about that next week, actually, depending on how much time I have left from talking about the other things. Yep.
But it's believed that the critical exponents do not depend on the lattice.
Yes, okay, that's an extremely important point that I failed to make. Yes, thank you. Yes, so that's a very important point. So one of the basic features of these conjectures is that with all of these things, what we believe is that these critical exponents and the scaling limits and so on, they do not depend on which specific d-dimensional lattice you take. So, I was talking earlier with the Lace expansion that if you, instead of using the hypercubic grid, use these so-called spread out lattices and then you can prove things, we really don't expect that to have any actual effect on the critical behavior of the model, right? It's just, it's often the case, our methods may be restricted to proving things about one specific lattice, but always the conjecture is that it doesn't really matter, okay? Now, there are, of course, some quantities that are affected by changing the lattice and others that are not. So, for example, the value of PC is absolutely will change if you change the lattice, okay? And in fact, this locality conjecture that me and Filippiso proved a few years ago, it really says that in some sense, the value of the critical probability is determined purely by the small scale geometry. So it's really like the opposite kind of thing, whereas all these things like critical exponents should only depend on the large scale geometry. Okay? That's, by the way, one of the reasons why you maybe shouldn't get too caught up in issues like trying to compute PC exactly, because it's, the philosophy in this area is that the universal things are the interesting things, right? So the things that do not depend on the choice of grid, that are kind of coming purely from things at large scales, purely from the scaling limit, those are the most interesting things to look at. Okay. And I guess a similar point would be, when we define these critical exponents, we often have these estimates that are up to constants, things like that. And, well, generally you would expect that you can replace this by some first order asymptotics, that this would be asymptotic to some specific constant over root n, something like that. Which is often important to understand if you want to understand scaling limits, but the actual value of that constant tends to be a non-universal quantity, so it's something you shouldn't try to understand too carefully because it sort of won't be interesting in some sense. Okay, but yeah, thank you. Yes, I should have said that sooner. Okay, so that's 2 dimensions, and of course, one could very easily give a whole series of lectures about the 2-dimensional results, which I won't do here because that's not the focus. So what about the remaining dimensions? So what about dimensions 3, 4, 5, and 6? Okay. Well, the first thing is that dimensions 3, 4, and 5, they appear to be very difficult to understand. So let me just put some question marks there, and I'll come back to this later. And I should say, one of the primary goals of this course is to tell you about the slightly different context of long-range percolation, where you can actually understand some similar kind of intermediate dimensional critical phenomena, but which you actually can understand. Okay, but let me leave this as just some question marks for now. This is something difficult to understand. What about dimension 6? So this is an interesting case in that in dimension 6 we have conjectures but not yet proofs, which I think is the nicest, most exciting place to be as a mathematician, which are... So the conjecture, and I should say, perhaps the better word is prediction, in that this is something that has the behavior has been computed using non-rigorous methods in the physics literature. So this is due to Essam, Gaunt, and Gutman. In the 70s. So their conjecture is that if you look at the volume tail, so generally speaking, again, for all these different models, you will have the same basic behavior that, we have what's called the upper critical dimension, which is 6 for percolation, above which you get the simple mean field behavior. Below the upper critical dimension, the exponents change. And at the upper critical dimension, you just barely start to feel the effect of being in low dimensions, which means that the scaling changes, but only by logarithmic factors. Okay? So, for example, the conjecture is that the volume tail, well, in high dimensions, it would be 1 over root n. In 6 dimensions, it is believed to be larger than that by a factor of log n to the 2/7. Okay. Similarly, if you look at the density of the infinite cluster slightly above criticality, in high dimensions, it would be epsilon. In 6 dimensions, it's believed to be larger than that, again by a factor of log to the 2/7. If you look at the susceptibility, i.e. the expected size of the cluster at the origin, again in high dimensions it would be like 1 over epsilon. In the critical dimension it should be larger by, again, log to the 2/7. So you might think that it's always log to the 2/7. It's not though. So for example, if you look at the 2-point function, so the probability x is connected to y, again in high dimensions this would be like the Green's function, minus d plus 2. in 6 dimensions, it's believed to be larger by a factor of log to the 1 over 21. Good. So let me say a bit about how this conjecture is arrived at and why we haven't been able to prove it yet. Well, there's a number of reasons why it's been difficult to turn this into a theorem. So the first basic difficulty, which is something that nowadays we at least some members of our community are able to do, is that this. So the way they arrive at this prediction is using a method from physics known as the renormalization group. Okay, and this is something that was developed most famously by Ken Wilson, who won a Nobel Prize for his work introducing the renormalization group. And as developed by Wilson, the renormalization group is sort of a systematic way for proving, or not for proving, for computing various aspects of critical phenomena in statistical mechanics. Also in quantum field theory, but let's stick to statistical mechanics. Okay, and generally speaking, by the way, as a point about the terminology, the word group that appears in renormalization group, just ignore the fact that you have a meaning of the word group as a mathematician. It's not really related to that. So the thing with the renormalization group, it's very technical to implement rigorously. So this has been done now for a number of models. So most closely related to this, Bauer, Schmidt, Bridges, and Slade, about 10 years ago now, were able to prove a number of theorems of the same kind of form as this for some other models, including what's called the phi-4 model, which is closely related to the Ising model, and also to self-avoiding walk. Well, not quite the self-avoiding walk as I described, but a variant of it called continuous time weakly self-avoiding walk. Okay, and so one basic problem with doing this kind of thing is just that doing the renormalization group rigorously is very hard. Okay, on the other hand, it's a kind of difficulty that we do know how to do now, in some sense. Okay, the more serious problem for doing this in the context of percolation is that it somehow doesn't really fit into the framework that people like to do renormalization group in. So the traditional setup for this renormalization group analysis is that your model should be of the form like a Gaussian field with some additional like weak interaction. So I'm going to be vague about what this means, but really the paradigmatic example here is what's called the phi-4 model, which is where you take the Gaussian free field, which is the sort of canonical example of a Gaussian random field on the lattice, and then you add in these quartic terms into the exponential that defines the distribution that gives you some. You sort of try to change the measure a little bit on the value of the field at each vertex. Okay, and basically all the methods start with a model expressed in this form, and then you try to analyze what this little interaction that you added in, what it's going to do to the critical behavior. And the trouble is, for percolation, we just don't have a nice way of writing it in this form that would be like the starting point for such a renormalization group analysis. Okay? Now, in the physics literature, there is believed to be such a way of writing percolation, but nobody has ever successfully made this precise exactly how it's supposed to work. And that's in terms of something called the phi-cubed model. And this is actually what's used in this derivation of these logarithmic corrections by SM, Gaunt, and Gutman. Okay? So one problem with implementing this is just we don't really know how to do that first step of turning percolation into one of these field theory type models. Okay, there are other ways of doing this. So another thing people do in the physics literature is there's something called the Potts model, which is a generalization of the Ising model, where you have, instead of just 2 spins, like plus or minus 1, you have a general number of spins, q. And there's formally a sense in which percolation corresponds to the Potts model with only 1, with q equals 1. Okay? So one way you can get these same values is that you study the Potts model, which is a sort of field theory in some sense, so it's more amenable to these traditional ways of doing RG. And I should say this is, what I'm describing now is not at all a rigorous way of analyzing anything. You analyze the Potts model, you derive the formulas for the logarithmic corrections and so on for general q, which is an integer that's at least 2, and then you just plug in q equals 1 formally into these answers that you get, and it does turn out to give you the same things as the other methods, and in fact these are almost certainly correct, even if this method is a bit dubious in whether it should work or not. Okay. Good. Okay. So one of the main goals of my lectures over the next week is to describe a way of doing the renormalization group for percolation, but with the caveat that it's only going to be for long-range percolation rather than this traditional nearest neighbor percolation. Okay, and the thing is, it's really not going to work like this. It's going to be quite different. So I'll say a lot more about that next week. Okay. One more thing about this, though. Another thing which physicists can do using the renormalization group is to say something about these intermediate dimensions. Okay. So this is an idea going back to Wilson and Fisher in 1972. So they had a paper called the Ising model in 3.99 dimensions. Okay, and the idea is, well, you know, these intermediate dimensions are very difficult to understand. 6 dimensions and higher for percolation is relatively easy. So why don't we take, instead of trying to understand this, let's say d is 6 minus epsilon. Okay, and then what they try to do is expand the value of the exponents as functions of epsilon. Okay, so for example, you get delta is 2 plus 2/7 epsilon plus 565 over 6,174 epsilon squared, etc. And eta is minus 1 over 21 epsilon minus 206 over 9,261 epsilon squared. Okay. So, you know, the first thing you might wonder here is, what does this mean? Okay, and in some sense that's the easiest, you know, that's the least problematic thing with implementing this as mathematicians. Though I should say there are a number of different things that you could mean by this. It's unclear which one is exactly the best way, the best interpretation. So I would say my understanding is that the way they think about these things in physics is more that you know, when you do the computations, you get all the sort of computations you write down, you get the dimension appearing as a parameter, and you can just sort of deform those computations you do by changing d continuously, even if you're not like interpreting what you're doing in terms of some actual probability model or anything like that. Another nice way of interpreting this kind of thing for us will be actually to work with long-range percolation, where you can do something very similar, changing not the dimension but something else which is very similar to changing the dimension, which you can do continuously. So these two things don't give you exactly the same answers, actually. Another thing you might be tempted to do as a mathematician is to study percolation on fractals, right? Now, I imagine there are lots of interesting things that could be proven about percolation on fractals, but I don't think it's the right approach for studying this kind of thing. Part of the reason for that is that the choice of fractal that you work on is highly non-canonical, right? There are a lot of fractals, and they don't only have one notion of dimension, they have a lot of different notions of dimension, and it's unclear which one the correct one would be. And generally I'd say percolation on fractals is interesting, but I don't think it's the right approach for this kind of thing. Okay, so some of the comments on this. One thing is that it's not at all the case that you actually compute the whole series. You know, what happens is that these coefficients get extremely complicated as you expand to higher order. And for example, in the physics literature, there's some fairly recent papers, one by Gracie from 2015, so 10 years ago, for example, where I think he computes these percolation ones to like the epsilon to the 4 term or something like that. And these get really, really extremely complicated very, very quickly. Okay, so it's really not that these methods are giving you the whole series. The other thing is that these series are believed to be divergent. So they're asymptotic expansions, but you cannot actually use them to just sum the series, evaluate with epsilon equals 3 or something, and just evaluate and get a value. On the other hand, if you take these expansions and you plug in epsilon is 1 or 2 or something like that, you actually get values of these exponents that agree quite well with simulations. So it's actually a pretty good way of doing things. Okay. One more comment. If you're paying very close attention, you might have noticed these two numbers, 2/7 and 1/21, are actually the same as these two numbers. And this is actually a general phenomenon that the logarithmic corrections you get, the power of the log at the critical dimension encodes the derivative of the exponent as you change the dimension to go below the critical dimension, i.e. the coefficient of epsilon, in other words. Good. Okay. So I'd say, in terms of percolation, this is still quite far away from being able to do anything like this. And of course, in the end, it may never really tell you anything, give you a theorem about these low dimensions. For long-range models, the situation is somewhat better. And in fact, for a different model called the spin-ON model, there are actually some rigorous results of this form by Slade and Lohmann and also with Wallace, where they are actually able for some models to compute these expansions to the first order. Okay. But so far for percolation, there's very little known about this. Okay. Okay. And I should say basically the problems with implementing this kind of thing rigorously, aside from this thing about interpreting what this means, which as I said is the less serious problem in some sense, the problems with proving this kind of thing are very similar to the problems that you have implementing this. I'd say that actually, there is a reason why you get the same numbers here, and it's tied to actually the computations that you need to do for proving this kind of thing, and proving at least the version of this to first order are actually very similar. Okay, but it's a strictly technically harder problem, I would say, than this problem. Okay. Check how I'm doing for time. Okay. Good. Okay, so the next thing I want to talk about is, why is the critical dimension 6? Okay, and actually I'm going to talk about this simultaneously with something else which is very closely related, which are the scaling and hyperscaling relations. So how should we think about this mean field behavior? You know, starting with a view to actually proving something. You know, well, for mean field behavior, the way that we usually establish this is in the following way. So we want that the susceptibility blows up like 1 over epsilon as epsilon goes to 0. Okay? And the way we usually establish this is by showing that the derivative with respect to p of the susceptibility is of the same order as the square. Okay? Once you have this, it's an easy calculus exercise to show that this implies this. Okay? So one thing that we always have is the upper bound. So where I'll write this curly inequality for meaning the same thing, that there could be some implicit positive constant here. Okay, now why is this? Well, there turns out to be a nice geometric interpretation of the derivative. Okay, so in general, if you have some function f, so I'll write omega for the whole percolation configuration, so you know all the data of which edges are open or closed. Okay, and let's say that f depends only on finitely many edges. In fact, it's one of these annoying things where almost every time we apply this formula, this won't be true actually, but you know the formula will still work. You just need to justify it with a bit of analysis. Okay, so Rousseau's formula says that if you look at the derivative of the expectation, then it's equal to some constant depending on p, which is something very simple, some rational function, but I'll avoid writing it because there's a risk I'll write the wrong thing. Some constant depending on p that will in particular be bounded away from 0, 1 when p is bounded away from 0, 1, times basically the sum over edges of how much f changes when you add this edge, when you flip the status of this edge. Okay, you know this really is just a very simple fact, calculus fact. It's not anything difficult to establish. Okay, and in particular, if f is the indicator of some event where a is increasing, actually we just call the set A increasing if this function is increasing, i.e. if you add more edges, if the event already held and you add more edges, then it continues to hold. So you could imagine this could be the event that x is connected to y, for example. Right. If it's increasing, then you can interpret this in terms of pivotal edges. Okay, so that means an edge E such that if I force the edge to be included in the configuration, then it belongs to A, and if I remove the edge from the configuration, then it does not belong to A. Okay, so of course being pivotal depends on the configuration, right, as well as the set A. Although note that one important thing here is that E is pivotal is independent of the actual value, like whether E is included in the configuration or not. Okay, and so we get that the derivative of this increasing event, again, up to some factors of P, which I won't write down, it can be expressed as the sum of the pivotality probabilities. Okay, and because of this fact that E being pivotal is independent of whether it's open or not, I can write this equivalently, changing the factor of P by like a P or 1 minus P factor to sum only over open pivotals or only over closed pivotals. Okay. So of course, if I look at the derivative of the susceptibility, right, well, I could write that as the sum of the derivatives of the probability that the origin is connected to X. Okay? And by Russo's formula, I could write this in terms of closed pivotals. So I have the origin, I have this edge which is not open, and I have X, right? So I can think of it as the sum up to constants as being the sum over pairs E and X of the probability that E is a closed pivotal for the connection to X, which again means that the origin is connected to one endpoint of E, the other endpoint of E is connected to X, and these two clusters are distinct. Okay? Now, what I can always do with these kind of sums is I can always change which of these points I think of as being the origin. Okay? So this is a special case of what's called the mass transport principle. So if I think, let's call these points A and B, which are next to each other. I can always exchange that whenever I'm summing over some collection of points with some configuration like this, it doesn't matter which one is fixed to be the origin. I always get the same sum. Okay, this is just like you can think of it as a version of like Tonelli's theorem or something like that. Okay, so this is equal to if I take this to be A and this to be the origin, and you know, whenever I fix one of these things and sum over the remaining points, it never the value of what I get never depends on which one is fixed to be the origin. Okay, now this is actually not true for arbitrary transitive graphs. It's related to the property of what's called unimodularity, and if you do percolation on arbitrary transitive graphs, there's often some case analysis according to whether you have this property or not, but in any case, it's certainly true for ZD, which will be the main focus of this. Okay. So in other words, what you can think of this as being is you have the expectation, you have the origin, and you have one of the neighbors of the origin, let's say origin prime, right? And you have this cluster here, let's call it K1, and the cluster here, let's call it K2. And what you're taking, the derivative up to constants is the same thing as the expected product of the size of these two clusters on the event that they're distinct. Okay, so this is a geometric interpretation of the derivative. Okay. Okay. So I mentioned that the derivative is always bounded above by the square of the. Yeah, there's a question.
Where do you get the product K1, K2?
Oh, right. It's sorry. It's because here I'm summing over A and B. Right. So the sum over A is the same as just taking the size of the cluster, right? B is a neighbor at the origin, so summing over, you can think it's the same as just fixing one neighbor. And then you're also summing over X, which gives you the size of the second cluster.
You mark K1 different? The intersection is empty? Or?
Well, the intersection is empty if and only if they're different.
Okay.
Right, because they're two different clusters in the configurator. They're two different connected components. Yeah, indeed. Yeah, this is the same as. Okay. Good. Okay. So, why is this inequality always true? Well, one way I could think about computing this expectation is you can think that I'll first sample the cluster at the origin, right? Now, if that cluster contains this point B, like or 0 prime here, contains this fixed neighbor at the origin, then of course I get 0, so I don't care about that event. Okay? If it doesn't contain this point B, then after I explore this cluster, I then have to explore this second cluster. But when I do that, I'm just working inside a subgraph, right? When I explored this first cluster, I found a bunch of open edges and a bunch of closed edges, but in the end, all the open edges are not available for this thing to use because they're on the other side of this outer boundary of closed edges. Okay? So you can think that when I explore this second cluster, it's equivalent to just doing percolation in the subgraph where I delete every edge that I explored in the first step. Okay? Now, of course, when you do percolation in a subgraph, you do get something smaller, right? Like in other words, you can run these two processes on the same probability space so that you always get a smaller cluster when you work on the subgraph than when you work on the big graph. Now, earlier I was warning you against that kind of reasoning, but that was, here we are always using the same value of P, which is why it is legitimate to do that. It's not legitimate to compare like critical percolation on a subgraph because you might change the value of PC. But if P is remaining the same, then it is perfectly valid. Okay, so because in this second step, I'm just doing percolation on a subgraph, I get something smaller. In other words, I get that the expectation of the size of this cluster conditioned on the first one and the event that they're different is always smaller than just the unconditioned expectation. So this is just bounded by the product. And of course, by transitivity, these are just the same. So I get the square. Okay, so this is always true. And if you do a bit of calculus, what you get from this inequality, that the derivative is bounded above by the square, this actually implies that the expectation always blows up at least like 1 over epsilon. And of course, this function, its derivative is of the order of its square. So this is saying, if you have the inequality version of the ODE, you're getting the solution, any solution to that differential inequality is bounded by the solution to the differential to the ODE. Of course, the only thing that's not obvious is how many times the sign flips when you do that. Anyway, this is a nice exercise. It's very, very easy exercise to check that the upper bound on the derivative of this form actually gives you the lower bound on the solution of this form. Okay. And the way you do that, by the way, is you just look at the derivative of 1 over f, right? So the derivative of 1 over f gives you this f prime over f squared thing. So, there you go. Good. Okay. So this is always true. And this, by the way, is one of a few examples in percolation where we see that in any dimension, the critical behavior is bounded by the high dimensional behavior. So this is an example of a mean field bound. Okay. And in fact, there are a number of these for percolation. So for the volume tail and for the probability the origin is connected to infinity, these also satisfy mean field bounds where again, the quantity is always larger than it is in high dimensions. The 2-point function, that's not true. So this minus d plus 2, of course, in 2 dimensions, that would give you 0. So you get non-decay of the 2-point function, which is, of course, not what happens in the 2 dimensions. Okay. Good. Okay, so for high dimensional behavior, the mean field behavior, the key step usually is to get the complementary estimate okay, which again you can think of as something about telling you about the model having weak interaction, right? It's saying that, these two clusters, they're always, this expectation of the product is always bounded from above by what it would be if they were just independent. And what you're saying is that in high dimensions, it's actually of the same order as if they were just independent. Okay, so again, it's a kind of non-interaction or weak interaction statement. Okay, now there are a few ways of doing this. So an important sufficient condition which was introduced by Eisenman and Newman in the 80s, is the triangle condition. So we define this triangle of P to be the sum over 2 points of the probability the origin is connected to x, probability x is connected to y, probability y is connected to the origin. Okay, so I should stress, this is really a product of probabilities of 3 events. It's not the probability of anything. Okay, and we say the triangle condition is just the statement that this sum is finite at criticality. Okay, and the theorem that Eisenman and Newman proved is that if this holds, then you get this complementary lower bound on the derivative. Okay. The proof of this theorem is quite easy when you have the stronger assumption that this is not just finite, but it's very close to 1. It can't be smaller than 1 because you get this contribution from x and y and the origin all just being the same, because you want. So if we imagine it's just slightly larger than 1, the way you can think about how this works is the following. So here's one way I could imagine sampling these two clusters. Okay? So I said before, a natural thing to do is that you first sample this cluster and then you sample the second cluster. Okay? Now, one particular way you could do that is you actually sample these two clusters independently, but then, of course, if they're independent, they might intersect or something. They're not really the clusters that you actually have in the model. But you can say, I'll sample these two clusters independently, but the first one has priority. So any edge that both the clusters queried, I'm just going to overwrite with the first one gets to actually write the value that it revealed when it queried the cluster. So that gives me this configuration with these two clusters, but let's say the first one looks like this or something, and then the second one does this. Then this region where they intersect, you use the values that you computed in the first step, right? Now, of course, this pair of clusters might look like this or something. In which case, when in the actual configuration, when I look at this second cluster doesn't really correspond to any actual cluster in the true configuration, right? There's like this bit, but then there's also this piece over here that's actually a separate cluster. Okay, but what you always do have is, first of all, this has the correct distribution, right? You haven't sampled the whole configuration, but you can sample the remaining edges with some extra coin flips if you want. And this configuration you get by first sampling this cluster, then this one independently, and then just giving this one priority to write the values of the edges that it saw, does give you the correct distribution. You get a percolation configuration that way. Okay. Moreover, in this coupling, if let's say this is the origin, this is y, so we explore the cluster at the origin, then this independent cluster of y, and then do this overwriting rule. If y is not in the cluster at the origin, and x is connected to y in the independent cluster, then x is actually connected to y in the real configuration if and only if there exists a path x to y in the independent cluster which is disjoint from the cluster at the origin. Right, hopefully that's clear. It's just, that's how this coupling works. Okay? These 2 points are connected to each other in the independent cluster, but not in the real cluster of y, because every path that you take from here to here is blocked by the other cluster. Whereas these 2 points are connected in the independent cluster and in the true configuration. Okay? So, why is this related to the triangle condition? Okay, so what we can do is we can do inclusion-exclusion, right? Now, or I guess more accurately, what's called the Bonferroni inequality, which is where you lower bound a probability by just doing inclusion-exclusion to the second term, right? Now, in fact, the Lace expansion that I mentioned earlier, one way you can think about the Lace expansion is it's actually a way of implementing inclusion-exclusion in this kind of thing, but actually to infinite order. So I won't be talking about that, but that's essentially what the Lace expansion is doing. For us, we can just say, well, we can lower bound this probability by the probability that the origin, so what probability do I actually want to look at? So let's say, let's look at the probability that the origin is connected to some point z. Y is our neighbor at the origin. Y is connected to some point x, and the origin is not connected to y. Right? And then we want to sum this over z and x. Okay, and this is our derivative essentially, right? This is this picture. Okay, well, each such probability we can lower bound by the probability that the origin is connected to z and y is connected to x in the independent clusters. So again, in this coupling, minus the probability that the same thing still happens, but the event does not hold. Well, I guess this is not, sorry, this is not an inequality, this is just an equality. Okay. Now, of course, when you look at this event that just concerns this pair of independent clusters, well, they're just independent, so you can just factor this, right? So this term here is the probability the origin is connected to z times the probability y is connected to x. Okay, just because we took these two clusters independently. Okay, now what about this error term? Well, you know, this is what I was saying. It's like you have the origin has to be connected to x, and y has to be connected, sorry, z. Y has to be connected to this point x, and the bad thing happens when this cluster also intersects actually every path between the origin and x, right? If that happens, then these 2 points won't really be connected in the true configuration. Okay. So the idea, you know, why this triangle condition is relevant is what you can do is you can sum over the specific choices of these points here. Okay? And you can see in this picture there is this triangle, if you like, right? There's the connection from the origin to A to B, B to Y. Okay, and that's sort of why this triangle appears in this thing. Okay, so how would you actually bound this? I realize might be. Sorry, I'm over time, I think, for this morning. So I'll continue this this afternoon. Thank you.
I was puzzled by the conjecture to stake it in the dimension 6.
Yes.
Because they make sense only if we know that there is no percolation at critical time.
Yeah.
So, which is not known yet.
Yeah, I guess, you know, it's often the way these things go, though, like, for example, in high dimensions, right, we know that there's no percolation at criticality, but only via this proof that actually establishes the full critical behavior. You know, it's not like in the Haaron-Seid proof you first prove that there are no infinite clusters and then you analyze them. It's you do everything all at once, and it's quite plausible that any analysis of 6-dimensional percolation would also have that feature. So I can say in the context of long-range percolation, which I'll talk about, there actually were purely qualitative results proven by Noemberger that showed that the phase transition is continuous, that you don't have any infinite clusters at criticality. But and then there are the later results of myself that I'll talk about that give you quantitative understanding of the critical phenomena. But the quantitative results don't rely on the qualitative results. They always reprove it. It's sort of, I can't think of any circumstance where it was actually useful just to know the qualitative statement in order to prove the quantitative statement.
Okay, no other question?
Yes. Maybe just a quick question. So for Ising, it's the critical dimension is 4.
It's 4, yeah.
And the type of diagram is slightly different, no? The one you look at, or I forgot?
Yeah, indeed. In Ising and also self-weeding walk, you get the bubble diagram instead of the so you know the diagram that looks like this instead of the triangle, and that, you know, I'll finish this afternoon telling you about why this leads to the critical dimension being 6, but it's very similar for those models. You get 4 being the critical dimension because the relevant diagrams are different. And in the lattice trees, for example, the relevant diagrams are the square diagrams, which is why you get critical dimension 8.
Okay, let us thank Tom again.